Who knows what distributed computing is? Wow, that's perfect. So let's see. Our topic today is distributed computing in general, and in the examples it will be Hazelcast. So I was, like 2 weeks ago, I was in Brazil. And I guess all you people know that Brazilian people love to dance and kind of things and are very eager to do something. So that is what happened at the Jugs. And I'm looking forward to do the same things here. So everybody stands up. We have a lot of free space here. Everybody stands up and does some dancing. No, I'm just kidding. You're still seated. Okay. But the important thing is interactive. So we're going to make this an interactive discussion. And for that, we first go to play a game. I see some weird faces. People are not exactly sure what's coming. So the rules for the game are easy. I'm going to ask a question, and everybody says yes. These are normally the kind of questions you don't want to answer with yes, but in this case you want. Believe me. So, did everybody read that? Perfect. So let's go to the important part. So I'm Chris. I guess in Spain, Christoph kind of works still. In Japan, it doesn't work. In a lot of other countries, it don't. Or it either. So just go with Chris. I did a lot of Java stuff in the past. 90 plus years is not exactly true anymore. It's like 11, but I stopped counting, I guess. Most of the time, these weird things like performance, GC, any kind of optimizing fairy tale in Java. So whenever something is going slow and the system doesn't behave the way you expect it, just give me some money, I'm coming over. I love to come back to Spain, so just hook me up. I'm Apache committer. Unfortunately, the project I worked on is now in the attic. Does anybody know what the Apache attic is? That means it is pretty much like that. There is no commit activity anymore. There is no recent community anymore. Unfortunately, that happened to us because everybody was kind of involved into other things. But the project was direct memory. It is an off-heap cache, on-heap cache. It's completely Java. It uses a lot of unsafe. Whoever figured out the unsafe discussion in the last weeks. If anybody wants to reactivate it, just go ahead and tell the guys we're happy to get it back from the attic and get it live again. There is some word gaming. We're here at the Google campus, so I expect some people to play games. Who's a gamer? Some people. When did you start? 1980? 1981? Perfect. So you probably would love the magazine I just read in the airplane. It is a German. Let's see. I hope you can see that in the back. It is called Retro Gamer, and it talks about all the games from 1980 to 2000. It's a pretty cool German magazine. Unfortunately, you have to read German. So yeah, I worked at Ubisoft doing game servers, high-performance game servers, and kind of things. So again, we're coming back to performance. I was performance engineer. Travel management. I'm not sure. Do you guys know HRS, Hotel Reservation Service? No? That's like the Expedia in Germany. It's an international company, but somehow nobody outside Germany knows it. Kind of weird thing. But I worked, again, in performance engineering. I did I made sure that the system, we rebuild it, that calculates all the rates and tries to get all the things right, is performing well. Kind of the same thing again. So in general, you see all this kind of ends up doing weird performance things. Who does performance, by the way? Like performance optimization, GC optimization? Okay, perfect. So at least some people. You guys know what I'm talking about. So maybe I don't have a chance to come back. Hello? My battery just died, did it? No, it didn't. Okay, so if somebody wants to see some nice blog posts, reasonably often updated, like every 2 months or something, this is one of the addresses for my blog. So when the new top-level domains came out, I had the feeling I have to get that. So let's get back to distributed computing. I think everybody agrees that you guys have a data center at home. Who has a couple of old computers? Who has a PlayStation? Oh, so all you guys have some nice computing device. I guess you all updated to the recent, or at least for PlayStation 3, for the recent operating system version, so you can't run Linux anymore. You're not alone. There are a lot of universities did that. So they bought a lot of PlayStation 3 because they thought, hey, cool, we can run Linux on it. And what happened? Sony decided, hey, when you can run Linux, it also means you can run games, copied games. No, we don't want that. Let's remove the Linux capability. And a lot of universities now have a lot of useless PlayStations. If you really want to get a nice PlayStation 3 that is almost not used, ask your local university. So the thing here is that is pretty much distributed computing, even though it doesn't look like. If you would use all those computers or servers or whatever you called them, and you would make them compute together, you would have a distributed computing data center. We're at Google, and that is kind of what Google started in the beginning when they were at the university. Does anybody know the pictures? The first computers that were kind of captured everywhere where they could? That is kind of the same idea. And it gets further. So that is what we had like last year. But we're modern, we're going further, so that is what a normal data center will look like in the next few years. Especially, Germany is proud of its intelligent power grid. I'm not sure how it is in Spain. So in Germany, we install an intelligent power grid, which can figure out whenever there is some power needed, and it figures out, hey, now this area doesn't need any power. It's midnight. It's very unobvious that the guys don't need power, so we can produce less power. I'm just waiting for the first virus. It will be pretty nice, so just plug in your power plug and install some virus into the power grid. That will be cool. I'm pretty sure someone is working on that. But here again, all those weird things, does anybody disagree that all of them have computers? We're living in a very, very weird world now, or in a weird time. All of those things, even a cattle, has some kind of a microchip computer. All of them are kind of updatable. I mean, a couple of years ago, we started to update our washing machine programs. Like, what? Why? Well, they figured out, hey, we can save some more water. So maybe we do a firmware update for our washing machine. Well, okay, fair enough. But, I mean, we saw that some people here already know what distributed computing really means, but the others don't. So maybe somebody can try to explain what distributed computing means in his own words. Who wants to try? Not so many people. I don't want to, so it has to be someone of you. We're making it interactive. I think everybody knows the word interactive. It means I'm doing it wrong and you say the right thing. Okay, so distributed computing basically means you take an algorithm which normally runs sequentially somehow on a local machine, and you figure out how to make it distributed, how to run in parallel, how to run on different machines, and how to merge all those different intermediate results together in the end. So that sounds very artificial, but we'll figure out what it really is in code. Do some people here work at Google? No. Okay. That's sad. I would really like to hear from some internal engineer how it works. So for Hazelcast and most of the other systems, I'm German, so I definitely have to have some beer. So it means you want to scale out. Scale out, as I said, you want to distribute your algorithm to multiple machines. You want to run them in parallel. There are still some companies trying to tell you that scale up is the right approach. Whenever your system's going slow, they definitely have something bigger to sell you. It's normally twice as fast, but triple as expensive. I'm not talking about Oracle. That would be too obvious. But I think everybody gets a point. So, for Hazelcast, it also means we're doing in-memory computing. What does in-memory computing mean? Well, in the beginning, it means in memory. That means we keep everything in memory. We keep as much in memory as possible, because that means it's fast to access. I think everybody agrees with that. But it also means you need a lot of memory. To get a lot of data into memory, you need a lot of memory. Happily, we're in a time, and we'll see that on the next slide, we're happily in a time where RAM is not as expensive anymore as it was in the past. Oh, okay, wrong order. Let's go to that one first. So we see that we definitely can't go as fast as L1, L2, and L3 caches, depending on the CPU. Whenever you have whenever you find a CPU that is reasonably cheap and that has a terabyte of L1 cache, please tell me. I'm the first one to buy it. So far, I haven't seen it, unfortunately. But we see that main memory with 100 nanoseconds is still quite fast. The interesting thing for me here is that when we send data over 1 gigabit Ethernet network, we're still amazingly fast compared to any kind of SSD. We're not talking about the spinning disk, and we're not talking about the normal internet latency. I think everybody knows internet latency. We had some gamers here. I think everybody knows latency. But as I said, so 1 gigabit Ethernet, it's 0.01 millisecond for a round trip in a local network. This is just a gigabit network. For our local test lab, we have 110 and 40 gigabit solar flare cards. Does anybody know what solar flare cards do or how they work? Okay, so compared to the normal 1 and 10 gigabit, solar flare cards bypass the Linux kernel stack for Ethernet and handle everything in hardware. That means they are very fast. And with the 40 gigabit on a 10-node cluster, we're going down to, don't let me lie, I think it's 23 nanoseconds round-trip time. So whenever you have some memory left and you want to make operations happy, buy solar flare cards. Unfortunately, you can't run Hyper-V or any kind of Microsoft technology. I mean, who wants that? Who wants to run Java on Microsoft? Don't put your hands up. So actually, so as I said, solar flare cards are nice. There is a nice story around it. Our data center where we host our test lab is in Turkey. So Hazelcast started as a Turkish company. We bought the cards in the US, and nobody would expect to have any problem sending it from the US to Turkey. Fortunately, it is a problem. It just took a half year to get it through customs. Maybe we're sending some bombs over. I mean, it's very typical that the US sends bombs to Turkey. I don't know. Just as a side note. By the way, it's definitely war. So, as you guys can see, I'm working for Hazelcast, and I'm working some more for Hazelcast, and we don't have underwear yet. But I heard we're working on that. So, let's get back. Okay. As I said, RAM is not expensive anymore. This nice slide, and that's why I asked about 1980, starts with a typical RAM value of 625 kilobytes. I think someone said we never will need more than 640 or something. Something like that. He kind of was right. Kind of. So by now, we're 16 gigabytes. This is home computer, by the way, home computer. So 16 gigabytes was in 2013 was kind of the standard, 8 to 16. I guess that's what still is common. My computer at home has 32. I guess I'm at the top level maybe. But the important thing is, if the other nice diagram shows the price per megabyte. And in 1980, 640 was kind of affordable, but if you got up to a megabyte, that was like $6,500, $6,500 for a megabyte of RAM. That kind of sounds like what we have today. Today we're at less than a cent, a half cent about. I'm happy that I'm not living anymore in 1980. So, but the important thing is, if we have multiple computers and we want to keep everything in RAM, it means we kind of have to distribute data. So data distribution is kind of sharding. Do we have database admin here? No? Perfect. So that means I can't insult anyone. That's perfect. So who knows the term sharding in the relational world, relational database world? Some people. So you saw some database admins whining and crying when you mentioned sharding? Perfect. Kind of. Very, very nice. So data distribution is not a new thing. People found out that data distribution makes sense, even in the relational world, because database systems were too slow. The problem is how relational databases are used to shard data. Sharding in a relational world is you have multiple relational database systems, independent, and you kind of do some number ranges. That's the easy way. So you say everything from 0 to 1,000 goes to that machine. Everything from 1,001 to 2,000 goes to that machine. That kind of makes a problem when you want to join the data, but we're just looking over that because we don't use relations anyways, right? Who uses relational database with relations? Nobody. So let's just use it as a key value store. The problem is not scaling up. Scaling up means we'll just add another number range, start a new machine. The problem is scaling down in this case. Scaling down means you start with 5 machines and you go to Mexico. And you figure out, oh shit, Mexico is not big enough. There are not a lot of customers. We would be fine with 2 machines. Okay, so now you ask your operation guys, please write a Python Perl PHP script which figures out the new number ranges, copies all the data to the right machine, and kind of makes everything working again. People love that. People really love that, especially the PHP programmers. There are a lot of really good ones out there. Facebook has all of them, I guess. So the thing is, what is kind of weird for the relational world and kind of works against the relational idea does work for all these systems that were meant to distribute data. Hazelcast is one of them. Most of the NoSQL systems these days do it. So they are able to scale up and scale down on purpose. Whenever you need something, or on your demand, not on purpose, on your demand. So the underlying system takes care of how the data are distributed and where they are. And that is the important thing. You don't want to think about it. And I hope there's the right slide. No, it's not. Wrong presentation. The other presentation has some cake cut it in different pieces and some sticks on the different pieces. So you want to have data distributed and you want to access them easily, which means you don't really want to know about this data distribution. With database sharding, you have to build it on your own, or at least you have to create those kind of rules how the data are distributed. For the good systems, you don't think about it. For Hazelcast, you just use a Hazelcast map, and the whole distribution, the whole serialization, the whole transmission between the cluster you don't see that in the best case. So how does it work? And that is very specific to Hazelcast, but all these systems kind of work the same way. So we see, it still says JCP tour. As I said, I was in Brazil. And it's talking about the t-shirt delivery. We figure out in the future, in the near future, why. So as I said, we're taking a normal map and we're putting our key and our t-shirt delivery into it. And what Hazelcast does is we're taking the code, we're doing a hash code a consistent hashing, not the Java hash code. That's important. And then we have a number of partitions. And the number of partitions is bigger, hopefully bigger than the number of cluster members. I'm talking later why. And then we just we calculate it with the modulo operator, and we get some partition ID. And since we have a consistent hashing, it means we always get the same partition ID, we're always for the same input value. And that is the important thing. It must be consistent hashing. Then you get the partition count, in this case, is constant, because there are systems out there that give you the option to change the partition count at runtime. It kind of doesn't make sense because you have to redistribute everything. It's like the nice relational word sharding. You don't want to do that, especially not at runtime. It doesn't make difference. You can just shut down, restart. You have to move anything. And the good thing about this idea is you can do some smart routing. So Hazelcast has two ways of deploying the system. You can either embed it into your system, so every of your application is a cluster node in itself, or you use a more database-like approach. You have a separate running cluster, and Hazelcast uses clients to connect to the cluster. Something like a JDBC client. And the good thing, if you have that, and the client knows exactly where partition ID belongs to which member, it can send it directly to that. And we're trying to do this as often as possible. So we're trying to reduce all the network round trips to the absolute minimum. Whenever a cluster member is not reachable directly, we're still rerouting, but you don't want to do that in the best case. So don't try that. So, demo time. And I'm happy, now I have another microphone. Woo! And I'm happy you don't look that. Not yet, at least. And you saw the next joke. Damn. So let's see. No, we're starting with something new. Test. Test is always a good name for a class. So the first thing we need to do when we start using Hazelcast is we need to start up some Hazelcast cluster. A Hazelcast cluster is, let's deactivate Wi-Fi again. A Hazelcast, so who knows any kind of competitor, like InfiniSpan or Oracle Coherence? Oh, InfiniSpan, have you ever tried to set it up? A long time ago. It didn't get better, believe me. It's still the same worst world experience. So the problem with InfiniSpan is it is a nightmare to set it up in JBoss, where it is integrated. You have to make that in quotes, integrated. If you try to set it up in a standalone application, it's like impossible. We tried it for 3 weeks and then we gave up. It's a nice experience if you want to hurt yourself or something. So setting up a Hazelcast cluster is as easy as, whoops, not this, that one. So all of our entry points are the Hazelcast instance. The Hazelcast instance offers you the entry point to any kind of data structure Hazelcast has. So we take Hazelcast instance, and everything we do is that one. We say, hey, please create a new Hazelcast instance. And if we start that up, we hopefully, whoops, wrong one. We hopefully see, whoops. Whoa, we have a Hazelcast member. A Hazelcast member, a single member cluster. I think that is exactly what we wanted, right? A single member cluster. Maybe not. So the nice thing about Hazelcast, by default, we're using multicast to discover other nodes, which gives you a nice out-of-the-box experience for testing, for development. So that means when I start it up a second time, we see we have a 2-node cluster. If I start that up a third time, who can guess what happens? Ah, perfect. Everybody's laughing. That's what I like. So as I said, we're making this interactive. Whenever I do a mistake, you have to tell me, right? So that means interactive. So 3-node cluster. Okay, so far so good. Now let's take something cool, or let's make something cool. We know how to create Hazelcast clusters. So far so good. we know how to write Java code, don't we? Who's not a Java developer here? Come on, guys. How can you not love this language? What do you prefer? Python? Scala. Go. Where'd Google? Go. Sorry. Dart. Ooh. C. Oh, man. C. OK. I can't show you an example with C. But we have a C++ client. So quite close. So we have a map. And what normal Java developer knows how to create a Java map, right, is a hash map. How do we make this multi-threaded concurrent hash map? I heard it somewhere. I don't know who it was, but I heard it. Perfect. So concurrent hash map. Still, we have some Java code, so we can put in some data, right? You have to tell me when you disagree with something. Come on. Now we get it. I think that kind of works. I haven't done Java for a long time, but I'm pretty sure that kind of works. Well, no compile errors, it looks good. So how do we make this distributed? Well, still, it's quite easy. And we just say, Hazelcast, give me a map, and we give it a name that we want to refer to. So the nice thing about Hazelcast, and I now need to take my microphone again because I'm walking around. The nice thing about Hazelcast is we're implementing the standard Java class library. So most of the collection API, most of the concurrency API. That means that it really is a standard Java hash map. It actually is a concurrent hash map. We see that in a bit. That's kind of weird with switching all the time. OK, so we can start that up. And who can guess what happens? Well, we start up a Hazelcast cluster. We have a single node, and we're putting in some data. So the only difference, and I know you don't recognize that. That's why I'm telling you. The only difference is we see that the cluster says, hey, somebody wanted to do something. So now we have to create this partition table. The partition ID assignment where all the partitions assigned to a single member at the moment. That's a very good distribution. OK, so we leave that running. And since I'm telling you that you can access data in a different node because we distribute data, we're going to try that. Just give me a random number between 0 and 1,000. Let's take the standard one, that one that everybody says, 500. We can make it 499, whatever. It doesn't matter. So the thing is, if I start that up, we already seen it will create a cluster. It will join the existing cluster, better said. And we get a 2-node cluster. And what happens is, underneath, Hazelcast makes sure that almost half of the data, or about half of the data, will be moved to the second node. It doesn't matter. It doesn't need to be 499. Whenever it's not local, we're going to the other node, retrieving the data. But this is a totally separated JVM. And I can show you that we have a separated JVM. And it still retrieves the data. That's how easy distributed computing can be. And it still looks like Java code, right? Beside the way how you get the map. It's like a factory function. Everybody knows factories. Everybody loves them. OK, so that was kind of easy. But we're already distributing data, and we already do kind of distributed computing, the simple way. We're accessing data from a different point of the system. That is like a typical use case. Imagine you have a web service and some shared state, like session replication. That is like a normal session replication use case. So we already do that, or we already could do that. It's just a map, and you put in some data and retrieve it somewhere else. OK, so far so good. Now let's go back a bit. And let's say, OK, we're now in a distributed environment. That means my local node is not the only system anymore. Maybe someone does something, and I want to know about it, right? So let's put in some value every second, just to have something happening in the system. and we start this up again, and we already figured out it creates a Hazelcast node, blah, blah. So now we want to know something, what is happening in the cluster. We know that data are pushed into the map. So let's say, hey, I want to be notified. We're Java developers, or Python developers, or C developers. So how do we get notifications? Listeners, perfect. We're working on that. By the end, you will be the perfect interactive listeners. So for Hazelcast, it's an entry edit listener. And this is obviously fully generic, obviously. And it has exactly one method, kind of expected. Now we do our important business logic. That is hopefully what you normally do, right? Like we know we need to put everything into the log files, because then if an error happens, we can exactly see what was going on in the system. That is the first rule of a Java developer. Put everything in a log file. Obviously, by default, you don't do that. And still, we're looking for use case. So we have a listener. So what could be a use case for a listener? Imagine you have a web shop. We're going back to the web. That's where most of this stuff is going on. You have a web shop, and you want to send out confirmation emails whenever someone was so grateful and bought something in your shop. So you put your order into the map, and you expect some other system to take care of that and sending out this confirmation email. Fair enough, sounds good. Now we get to the IMAP. IMAP is the Hazelcast extension of a map. Actually, as I said, it's a concurrent map. So you get all the map operations, you get all the atomic operations like replace, whatever is put f absent, whatever is in the concurrent map, and you get the cool distributed features from Hazelcast. So whenever you need something special, you go to the IMAP. Otherwise, you do exactly what we learned as a Java developer. You stay with the interfaces you know that everybody loves, map, concurrent map. So the IMAP, as I said, has some extensions to do distributed computing. That means we can do distributed queries. So if we look, we have values, and we have values with an override for a predicate. That's pretty cool. So we can pass in some filter that is sent around the cluster, will be applied locally, and they all just send back whatever matches the filter. So that is cool. It's not exactly what we want in this case. So we are asking for an entry listener because we want to be notified whenever something is going on. I put in true. The second parameter, I'm not sure if we can see that. Probably not. It says Boolean include value. So I can tell the listener to send around the value inside of the cluster or to don't. If I'm only interested in the key, I don't want to send the value. Imagine you have 100 max value inside of your map. You don't want to send that around if you don't need that. In this case, we really want to see what is going on. So we start that up again. And it's connecting again to the cluster. And it actually starts to push in values. Let's make it a bit smaller. So we see the value, and we see the keys. The problem is we're not exactly where we want to be. If I start that up a second time, it will get all the values again. So imagine you have a 1,000-node cluster. You're a really huge web shop. I guess if you send 1,000 emails, confirmation emails to your customer, it was probably the last time he was grateful to you. So you don't want to do that. So we see that both events pop in everywhere. So we talked about data distribution. So that means we're moving around data, and we always have some node owning the data. So we have something else. Hazelcast is so nice to you and gives you an opportunity to just say, hey, only react on local events. So whenever I'm going to be the owner, please notify me. And if I start that up 2 times, we will see they connect together, and some events pop in here to 291, Some events pop in here, and the first node that is still running but doesn't have these listeners, it will also receive some of the objects. So that is what we want. We want one node sending the email and exactly one node. So now we're really doing distributed computing because our algorithm does exactly what we want, and it does it only on a single node for any kind of value. So that's pretty cool, isn't it? Ah, I see some heads nodding. Yeah, that's nice. So any kind of question to that? Anything you would like to see? We definitely have to work on the interactive. Okay. Okay. So let's get back to the joke you already seen. That was easy, wasn't it? So the important thing for Hazelcast is we want to show or want to prove that distributed computing is easy. It doesn't need to be as hard as all the other frameworks like to show you. To me, it feels like the other frameworks are designed to make expensive consultants. People coming to your company wanting a lot of money to tell you how its system works. With Hazelcast, we have the standard Java stuff. And even legacy applications are kind of easy to transform to Hazelcast and to make distributed. The only thing, whenever you have like a bad habit in your code, well, you definitely get to have a penalty. But you should have it by now already. Unfortunately, Java code doesn't really penalize people. So it is easy. If you want to be the consultant, don't tell anyone. Just make the prices. Okay, so we had data distribution. The second part, obviously, is parallelized computing. We already seen how to do some basic parallel processing. But if you want to calculate data, it is a bit harder. So this was a very easy reacting, but that already solves a lot of use cases. Parallel processing means you really send in data and you want to calculate them. A typical example in universities is gene calculation, something like that. So really huge data. Collected frequencies from the universe. What was the name of this software that was running on the PlayStation? It was also available for the PC, calculating some kind of university frequency. I can't remember. I don't remember the name, but that was like the perfect example of distributed computing. Everybody could run it on his local computer or on his PlayStation or whatever, and you got a piece of the data and you calculated it and you send in the result to be merged into the overall result. So that is what we normally do. So don't look at the code. It's not Java, it's not Scala, it's not Ruby, it's not Python, it's not C. It's kind of something that I made up to squeeze it on the screen. So we generate 100,000 random integers, and we store them in an array, and then we split it up into blocks of 10K. So we end up with 10 blocks, 10K elements each, and for every of the elements, we say, hey, please give me a sum of that block. So we calculate intermediate results. And then we take these sub-results, intermediate results, and we sum them up again. So pretty simple mathematical operation. It's an addition, it's a sum operation. I guess I don't have to explain how sum operation works. Perfect. So the important thing here is this for each. It doesn't really care if I sequentially calculate it, if I calculate it in multiple threads in parallel, or if I distribute it to multiple machines and just wait for all the results to drop in. And we again have this nice thing. Any functional programmer here? So no mutation. You heard about that, I guess. So all functional programmers are like, oh yeah, we do this for centuries now. We started with Erlang and whatever all those weird functional programming languages are. I guess you know better. So the important thing is you don't want to have mutation. Whenever you want to distribute things and to work on them in parallel, you don't want to have data mutation because it always means you either have to synchronize multiple machines or you have to at least synchronize cache lines and all those weird things you don't want to think about. So whoever tried to have a non-volatile field and have it updated in multiple threads at the same time, you probably know what I'm talking about. Okay, still works. So no mutation, just create new values. It's not as perfect for the JVM, obviously, we all know that, the Java heap and kind of things, but there were some people talking about a practical solution, hopefully. Value types is just one of them. So let's imagine that in the future, the JVM will be better in doing those kind of things, hopefully. And as I said, this for each means we independently compute data. And I already said it doesn't matter where I do it or how I do it, as long as I come up with the same sub-results. And these sub-results don't need to be the end. Java 7 was so nice to us to give us the fork join pool. Fork join obviously is one of the concurrency things that Hazelcast doesn't offer. I had a long discussion with Doug Lee, the guy that wrote the Java concurrency framework. And the fork join pool, unlike all the other things in the concurrency framework, is not an interface. It's a single class. It has exactly one protected method to override. It's very nice. And this one protected method doesn't give you the option to distribute it. So I had a long discussion with him, and he didn't realize what I wanted to do, and he always pointed me to this one method. I guess he was wrong. So what I expect, Hazelcast eventually will feature fork join pool. It will recreate this interface, or it will recreate the API in an interface, fork join pool, but it's not the Java fork join pool. But, well, it just means you can do work stealing, you can break it down further. You don't need to make 10,000 blocks. You can make it whatever you want. You can split it up even further. And you can redistribute it again. You can split it up, blah, 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 blah. It just doesn't matter. The algorithm is created in a way that it doesn't really matter how often you send the operation, how you send the operation, and how you distribute it or how you calculate it. I guess everybody agrees that this sounds amazingly easy for mathematical operations. But you would be surprised, it works for a lot of things if you really think about it. So for example, we're at Google, so let's look at how Google crawls, or Bing, when we go back to Microsoft, how they crawl websites. So you have a long list of URLs and an easy example, and you distribute every URL inside of a single task. And you just send them around. OK, so the URL is crawled, which means you download the HTML code, you create a new task, you put in the HTML code, and you send it again to the cluster. It doesn't matter if all the other URLs are already crawled or not when this HTML code is analyzed. You don't really care because everything is completely independent. And this is like this fork join. You split up this operation, which you could do in a single step, like using the URL, downloading, analyzing, writing. And you split it up into 4 different things. And you can distribute it. It doesn't matter. So that's what I'm saying is it works for a lot of things. You just need to think about it in a different way. You don't always have to do everything sequentially. That's the important thing. So again, demo time. Who knows who that is? You're like me. You're all too young. It's Evel Knievel. It rings a bell, right? We heard about this guy somewhere from our parents, I guess, most of the time. He was really crazy. He jumped over, was it 25 cars or something with a motorcycle? Something like that. Kind of weird person. So let's see. Processing. I recreated this stuff in Java Fortunately, in Java, it doesn't look as nice as on the slides. So I had to use some methods for that. Random kind of is easy. I guess everybody agrees with that. We create an array and we put in some random values. What is not as easy anymore is the split operation. Whoever wants to write that in Java 8 with the Stream API, I'm pretty sure it's easier. I haven't really looked into it. If you really want to, just give me a hint how to do it, and I'm gladly exchange it, because that is extremely ugly. That is what we did in Java for years, for centuries, for decades. And I guess most of us will do it for the next decade, maybe. Who's still on Java 6? Unfortunately, we are as well, yes. Because a lot of our customers are still. Your guys are not working at banks, right? That's very obvious. Java 7? Nice. Java 8? What kind of companies are you working for? Can I move? So yeah, in Java 8, it definitely will look nicer. So then we come to another thing. Again, Hazelcast. As I said, Hazelcast has all these Java concurrency and Java collection APIs. So we obviously have an executor service. That's a standard Java executor service. Again, thankfully, Doug Lee decided to make an interface. Woohoo! One yip hip for him. I hope he will decide to do those things in the future again. No idea why fork join is not. So again, you ask Hazelcast, the Hazelcast instance for your entry point. In this case, we ask it for data structure, which is an executor service, and we give it again a name. And it's very random that is, again, data. It could be everything. As long as all the nodes refer to the same data structure name, you see the same data structure. And I guess then it kind of gets easy. We know this kind of weird thing with the futures. Futures are not always a nice thing. But I guess if somebody uses Scala, there might be a better way to do it. In Java, as I said, who doesn't like this language, it kind of feels weird. So the important thing here is we have a sum task. And the sum task in itself is, first of all, a Java callable. And just to prove it, it is a standard Java callable. We do some calculations, so we take long as a result for in, because it might be that we overflow. We have to send it around the cluster, so it kind of needs to be serializable. I chose the easy way. You don't want to do the production. Java serialization is like the worst thing ever. That is like the Armageddon example. It must be the Armageddon person starting all that. In the end, serializable will be left. Maybe. And do we have some Spring developers here? One. That's two. That's unexpected. Normally, there are a lot of more Spring people. So Spring people are aware of those aware interfaces. That normally means you get some automatic injection of something. So in this case, Hazelcast instance aware is kind of self-speaking. It injects, after deserialization, it will inject the Hazelcast instance into this callable. And we do that to make it obvious that we distribute the operation. So we've seen that we have to send the data. So we send in some of these blocks, or one of these blocks, these 10K blocks. And here again, we use it, the Hazelcast instance, and we ask Hazelcast for the current cluster and for its local member, which is some kind of the unique ID inside of the cluster. It contains of the IP address and port number and kind of other things, and UUID and blah. And then we have this mathematical hyper operation. We sum up data. We already talked about, we don't need to explain that. And we return the result because we have a callable. OK, so we submit the operations. It's a standard executor service submit. Oh, again, here the proof. It's a Java util concurrent executor service. and we wait for the futures. We do this final sum operation, and let's remove that one and remove that one. We just want to have some Hazelcast nodes running. Let's start that up 2 times. Get some water. So our cluster started, and now we start the calculation. And we connect. And what will happen is that this processing thing, it sends the operation to all nodes and says, here is your piece of the data, please calculate on it. So we have this processing node, and it returns the number because he's the one that submitted the operations. And we see that's a fairly good distribution. So 3 and 5 is 8, and 2 is 10. So 10 blocks, 10K each. Our default distribution is random. I kind of disagreed with the fact that we want to implement our own load balancing algorithm, because everything you implement is kind of random anyways. Whoever tried to write his own load balancer? Nobody. Okay. Again, just a quick introduction to load balancing. I did it at Ubisoft because we had to load the players from an amazingly nice relational database called MySQL or something. It was obviously amazingly fast, blazing fast. And we stored the last point where we calculated the player, so whenever he came back to the game, we had to kind of fast forward the game to his current state, because it was a real-time game. So that means you have to have some startup time. You have to load the data from memory, from the database into memory. You have to calculate the player. You have to load probably a lot of other things around it, like friends and whatever. And that kind of takes time. So you definitely, if you want to have a good load balancing, you definitely have to know how long your operations will take, how long your data loading will take. So there is nothing like a general load balancer. Fortunately, and we are so nice to you guys, there is, let me see, there is a version of Submit which doesn't work. Let's see here. Oh, that's the reason. Again, we have an extension, and the extension obviously knows about a lot more operations. So there we go. There is a submit where you can put in your task, and you have a member selector. And the member selector is pretty much the interface where you write your own 10 minutes. What? Wow. Okay. So the member selector is meant to implement your load balancer. Okay. We see this running. Any question to that? No question. We have 10 minutes. Okay. Again, I'm from Germany. Who knows who that is? Come on. Fast, fast, fast. Perfect. Our chancellor, probably the best picture ever taken. I hope it's a real picture. It's not modified. I don't know. So the last part of distributed computing, that is kind of going back to the first part. It's distributed caching. And we have to speed up. So why do we want to cache? We collect and store data in memory. We're going back to the in-memory. And why do we do that? Well, because we want to access it whenever we have to, whenever we have peak times, when we need to be fast. So the squirrel is kind of the perfect example of caching. It collects the nuts in late summer and autumn, tries to hide them in a way that it hopefully finds the nuts again in winter, not like Sketch from Ice Age. Did he ever get the nut? I don't think so. So a bit fun with caches. Who knows what it really is? Flags, perfect. But I like the fun with caches example. So, evolution of caching. Who wrote his own cache in the past? Just 2 persons. Wow, 3, 4. You don't know if it was a cache or if it just was named cache. So the first way is obviously you create your own cache, and that is what happened in the past. A lot of people did that, and everybody ended up with something that looked like what he thought is a cache, or what the Americans think is a hamdogger. It's a mixture of hamburger and hot dog. It's a cool thing. You can really buy that thing. So caches are simple. At least the people that wrote their cache kind of agree. You have a class that hopefully is called cache because you want to make it obvious. You have concurrent hash map in there because we figured out that this is thread safe. And then you have put and map operations. In the best case, if you want to make it really, really, really obvious, you call them cache and retrieve, or cache and uncache, whatever. So that is a cache, right? Kind of. Okay, unfortunately, not exactly. We're currently only putting data and we're retrieving data. Most of the time you want something more. You want to know when data expires. So when you use a cache, you normally say, okay, I put in something and that is valid for a minute, for an hour, for 24 hours, something like that. A new site obviously recreates its cache all 24 hours because you want to have all the new articles hopefully pre-rendered because you don't want to render the same HTML all the time. Beside PHP programmers, they render all things all the time. So what you end up is something with time to live. And this code is only getting worse, so you don't need to read it anymore. The important thing is you store some creation date of the cache entry, and whenever you do a get, you figure out, hey, is the entry still valid? If not, remove it, return null. Problem is, operations doesn't like that because your Java heap is not going to shrink. As a good Java developer or C developer, we know what to do. We use a thread and do some auto cleanup. That's pretty easy, right? Everybody knows that. So you have, again, some running task, and he does exactly the same. He looks through the single entries, and he looks if the entry is expired, and if so, you remove it. Easy thing, just a single problem, and we're making this fast since I'm running out of time. So who figures out what is wrong? Come on, we have some distributed computing or performance engineers here, so that should be easy. It is not the remove. I make it fast this time. It is the iterator, but it's not the remove operation. Nobody? Okay. Does that ring a bell? Big O-N? What does it mean? The runtime will grow when you put in more elements. The more elements, the bigger the runtime. With a big Java problem or with an API problem in the schedule executor service, that is very common, or what is commonly happening. Schedule executor service is clear, right? Everybody knows what a schedule executor service is. And it has 2 different ways of scheduling tasks. It has with fixed delay and at fixed rate. What is the difference? You're nodding? You don't know? So that is one of the common problems. With fixed delay means it waits until the last task is finished and then it will reschedule with the delay. At fixed rate, it will just reschedule. That is not a made-up example. That was a long time in the Hazelcast code, and I hope that no customer ever used the expiration up to that point where we fixed it, which is, again, back in the past, but it would have been very, very embarrassing. So we started really testing it, and the system stopped with about 60 threads doing nothing like expiration. And it was like, what is going on? So that is the reason why caching is not simple. Even a company that works in the area does weird problems or does those weird things. And they're very, very common in most of the custom caches. Okay, sure, it was a trap, but as I said, it's not a made-up example. So we're going back to our evolution of caching. We've seen the custom caches and we've seen how they failed. After that, a lot of you know what I'm talking about, proprietary caches came up. Proprietary caches figured out, hey, we can fix those problems, but we don't tell anybody. Or they figured out, hey, we have those problems and we don't tell anybody. Whatever comes first. A lot of companies decided to go open source, Hazelcast, InfiniSpan. GridGain was open source, then it was closed source, then it was open source again, now it's Apache. It's kind of weird. So the GridGain story is kind of a different thing. It feels like there's a huge Wikipedia page talking about it, how they changed all this stuff. If not, you should definitely figure out the history of GridGain and write some. It would be nice. It's like the history of the S. But to be honest, a lot of the open source systems also have a commercial version. Again, GridGain, InfiniSpan, Hazelcast. Whoever, Gemfire, which is now Apache Geode, which is Pivotal, whatever. So all of these open source things also have some commercial version with extensions on top of it. And there's again this big brother thing from the Hulk slide, which is just stupidly expensive. That is not my term. That came at a conference like, I want to exchange this competitor of yours because it's stupidly expensive. Okay, so Jcache, who heard about Jcache? Java Caching Standard API? Perfect. So at least some people. So the JCP, the Java Community Process, created a caching standard. We kind of agree that caching is still, or the caching requirements are still kind of simple, even though the implementations might be not as simple as we think. The requirements are kind of true. The problem is, and we come back to this custom thingy, I think everybody knows how this happened in the past with all the mobiles. Like you have 4 generations of mobiles and everybody had its own kind of weird plug. The most expensive ones would be somewhere on the side. Apple had like 4 or 5 in the past. But the thing is, all those competitors and even your custom implementation, all of them have some kind of their own API. Hazelcast at least shares a lot with the collection API, but not all of it. We've seen all these extension interface because we kind of break the contract at that point. And Jcache tries to be this USB, micro USB port that kind of connects all those things. In the future, we figured out it will be USB 3C, I guess, right? The new thing that Apple also moved to for the MacBook. So Jcache tries to be this unique plug, and all of these other ones that are on top of it, all of them should have a Jcache implementation. Obviously, in a perfect world, you choose Hazelcast. So, normally I talk a bit more about it, but believe me, Jcache is success. It's not as successful as it could be because we had a bit of time pressure when we released it. But in a couple of weeks, for Java 1, we kick off version 2, and if everything goes the right way, version 2 will be like the last Jcache version ever. It's not like JPA, where JPA 4 still misses many-to-many relations, if you know what I'm talking about. So, the last 5 minutes, the shameless plug, whoever finds it can keep it for himself. Hazelcast in 5 facts. I already talked about most of the things. Java Collection API, Java Concurrency API, transparent data distribution. We've seen that in the example. Very nice. Drop-in replacement. We've seen that as well. And Rod Johnson, who knows Rod Johnson? We had 2 Spring developers. Oh, more people know Rod Johnson than we have Spring developers. That's not a good sign. He created Spring as a demo implementation of his book, JE without EGB, Java Enterprise without EGB, something like that. So Spring was his demo implementation of the book. Quite nice story. He's also one of our investors and board members, and he said when we talked to him the first time, he said, Hazelcast is disruptively simple. It's so disruptively simple that you might get it wrong, that you might forget that you're actually working on a distributed environment. And as I said, if you have bad habits in your code, you definitely get a penalty if you try to integrate it into your legacy application. Otherwise, it's a drop-in replacement. And when your code is nice, what I expect from 99% of all the applications in the world, it will just work. So that means time to be happy. We're Apache licensed. As I said, we're open source. We have an enterprise version. If you have to spend some money, just spend it on us. We're happy about it. I'm happy if I get my next salary. If you're happy with the open source version, we're happy as well. I'm happy to give a piece of my salary for the open source community. So Apache license, and that means, because I'm community lead, I say hazelcast.org. If you want to spend money, go to hazelcast.com. My colleague will be happy to talk to you. Otherwise, hazelcast.org, down, he's waving right at the back. So, hazelcast.org, download the jar file, download the zip file, take the coordinates and go to Maven, Gradle, SBT. Did I miss something? Any kind of other, sorry, make files are not supported. And just get started. That, by the way, wasn't really good in Brazil. They really don't like it. I don't know why. But I say you can do it. You've seen it's easy. So download it, get started, try it out. If you have questions, drop us a line. And if you want to have a nice Hazelcast t-shirt, unfortunately it's not that one. It's a new one. Go to bit.ly and t-shirt cast, put in your address, your name and email address, and we ship it to you. Any question?
I have one.
Yeah.
How do you do the multicast?
Sorry?
The multicast operation that you said that you use multicast to discover knowledge in the cluster.
Yeah.
How do you do that?
How we do that?
Do you use JGroups or?
No, it's a custom implementation. So the whole network layer is completely custom. It's a peer-to-peer network, and multicast is just used for discovery. But obviously you can disable multicast because it seems to be created from an evil mind. Network operators don't like multicast. It tries to kill your network or something. I don't know.
Yeah. And the question is, how do you solve when you want to deploy Hazelcast in EC2? How do you solve that? Because if you use JGroups, you need to use S3P, S3.
Yeah. So the question is, how do you solve discovery in non-multicast supporting environments like EC2? So currently we have EC2 discovery built in. With Hazelcast 3.6, which is the upcoming version in autumn, we have a new discovery SPI where every kind of cloud provider can write its own IP provider right to the system as a plugin. So we expect Microsoft to come up. As I said, nobody wants to run Java on Microsoft. They believe people do that, so they want to support us. We expect Red Hat for what is it, cloud, huh? Yeah, exactly. Or Cloud Bees or whatever is going on outside. So also we have one customer who's going to implement a Zookeeper lookup. One person from the community from Google, who's not here today because they're somewhere in the US, does Kubernetes implementation. We're looking forward to Docker implementation, so it will definitely be the way to go in the future. Any kind of other question? Okay, then in a more Brazilian way, obrigado. And I hope that was right.